So whenever we try to verify trig identities, you have to make a decision. Do you want to make the left look like the right or the right look like the left? It really changes from problem to problem, and it really is a personal preference. Me, by looking at this one here, I could go here to there or here to here. Again, it's your choice. I would probably try to turn this into that. I'm thinking I'll do something with tangent. Look, we like sine and cosine. You see where it says tangent? Nuh-uh. Instead of tangent, you know tangent is sine over cosine. So I'm probably going to make this to look like that. I usually choose to make the one that looks more complicated look like the one that's simpler. This looks more complicated than that. So I want to make the one that looks harder to look like the one that looks easier. To me, this just looks harder than that. So I'm going to make this look like that. And as was just mentioned, instead of tangent squared, write this as sine squared over cosine squared. And I'll leave that there because I like sine and cosine. We try to change like tangents into sines and cosines. Try to turn things into sines and cosines. This stays as is because I'm not going to touch that. I'm going to play with this here. Now, why don't I drop a 1 below here? So what we have now are some fractions, fraction minus fraction. And remember that if you want to add fractions or subtract fractions, you need a common denominator. These denominators are not the same. So what I'm going to do is I'm going to make them the same. I'm going to multiply this by cosine squared theta, multiply by cosine squared theta. There it is. And so here on the left, we get, that stays the same. So this is sine squared theta over cosine squared theta minus, look, that's going to be sine squared times cosine squared. Sine squared times cosine squared. And in the bottom, I have cosine squared. So what was the point of even doing that? The point of doing that was to get a common denominator. And now that you have the same denominator, two fractions become 1. Where the bottom stays the same is just cosine squared. And in the top, you have this here. We have sine squared minus sine squared cosine squared. And again, this just stays the same. So now look here at the numerator. If you notice, they have two pieces, but they both have a sine squared. So what you can do is you can take out a sine squared from the top. Okay, and let's make sure that you actually believe what I have. Is this the same as that? Well, look, if you distribute in your head, this times this is that, and this times this is that. So for sure, going from here to here was okay. Now the next part is the key part. This is like the tricky part. So let me grab another paper and remember this identity. Let me just pause for a second. Remember that one of your fundamental identities is that sine squared plus cosine squared equals 1. This is true. But what you know what you can do is you can manipulate this however you want. And me, I feel like moving cosine squared to this side. Because if I do that, I'm going to get this here. Yeah? If I move that to the right, that's what it becomes. And this is also true. So wherever you see 1 minus cosine squared, you can erase it and instead write sine squared because those two things are equal. So I did this because look. Right here in the parentheses, what's it say? 1 minus cosine squared. But you know what? Nuh-uh. Instead of 1 minus cosine squared, I'm going to replace it with sine squared. So watch. That one stays the same. But then the stuff in the parentheses, whoosh, it's gone. And it gets replaced by sine squared. And in the bottom, you have cosine squared. Now here in red, look, right here. Sine squared over cosine squared. Sine squared over cosine squared. That little red bubble, that's just tangent squared, yeah? That's just tangent squared. And this just gets copied and pasted. And then if you look, boom, 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 boom. You see that? Look, this left-hand side, all this craziness we did. Now the left perfectly equals the right. And so we're done.